Hello and welcome in our YouTube channel Metallurgical Fact. So this is the eighth part of RINL-Vizag Management Training Exam 2020 practice of metallurgical engineering. Before this, we have given 7 part of this video series, and if you did not watch those videos, so you can go through the RINL-Vizag Management Training Exam 2020 playlist, and you can watch those videos. That videos will be very beneficial for your GATE exam, also for RINL exam, and that will be beneficial for clearing your concepts in metallurgical engineering basically. So this is the part 8, and we will do the practice of some metallurgical questions in this video. So the first question of this video is: critical resolved shear stress in single crystal is calculated by applying. So they have given 4 options, that is Bragg's law, Coulomb's law, Hooke's law, Schmidt's law. Okay, so this Bragg's law, we will see the options, we will cross check the options, which option is correct. I suppose I don't know which law is applicable for critical resolved shear stress in exam. Okay, suppose so this is practice, so we will eliminate the options. So the first law is Bragg's law. So you must have heard about this law, that is Bragg's law. Bragg's law is basically for related to the X-ray diffraction. Okay, so this X-ray diffraction we have done numerical based on this Bragg's law many time in previous parts. So this Bragg's law is basically 2d sine theta is equals to n lambda, and in this case I have already told you this d is interplanar spacing, and this lambda is wavelength, and this theta is Bragg's angle, and this n is order of reflection. Okay, so this is not correct, this is basically for X-ray diffraction. So the next law is Coulomb's law. So Coulomb's law is related to the stationary charged, and in that Coulomb's law what we get, we identify the force acting between the stationary charged particles. Okay, so what we know about this Coulomb's law, this is the formula 1 by 4 pi epsilon naught multiplied by q1 multiplied by q2 r square. So this is the, suppose this is the positive charge and this is the negative charge, this is stationary, and distance between this is r. So we can identify the force acting between this charge is by this Coulomb's law. So this is related to the electrostatic principle, that is electrical kind of things. Okay, so this Coulomb's law is also not correct for this question, and this is also not a relevant option for this question. Okay, so C option is Hooke's law. Hooke's law, we all know Hooke's law is basically the strain of the material is proportional to the applied stress, means stress is proportional to the strain. So this is stress proportional to the strain within the elastic limit that Hooke's law represents. Okay, so this if we will remove this proportional sign, so some constant will come, and this will be E epsilon. So this E is basically Young's modulus or elastic modulus, we know. So this comes from the Hooke's law only. Okay, so this is the Hooke's law. So this is also not correct. This is for stress strain, relating to the stress strain something. Okay, so the last one is Schmidt's law. We will see what is the Schmidt's law in short here, and one video I will give on this topic. This is very important in critical resolved shear stress point of view. Okay, so here I will make you understand by the short method, that is, this is known as Schmidt's law. Schmidt's law formula is basically tau RSS. This is also known as shear stress. This is resolved shear stress. That's why I have written in RSS. Okay, so this is tau RSS is equals to sigma cos theta multiplied by cos phi. Okay, so there is two angle. This is, one is theta, one is phi, and this sigma is strength. Also, you know, this is the stress. So this theta, one of the angle is the angle between the slip direction and the tensile axis. Okay, so slip direction I will show you in upcoming video how we calculate this, how we derivate this formula. Okay, by the diagram. So here but just for understanding, you can understand that this theta is slip direction, angle between the slip direction and the tensile axis. Okay, so this is the angle theta, and the phi is basically the angle between the normal to the slip plane, and and the tensile axis. Okay, so tensile axis is common in both cases. So this angle is basically slip direction and tensile axis angle, and this is the angle between the normal to the slip plane and to the tensile axis. Okay, so this tau CRSS is something which relates the critical resolved shear stress in single crystal. Okay, so this option is correct for this question. So Schmidt's law is correct. So this is how we check the every options in this question, and we identify that this Schmidt's law is correct answer for this question. Suppose if we don't know about the Schmidt's law, then also we can tick in exam by eliminating three of the options, because we know these basics rules and which is applicable for which area. Okay, so we can eliminate these options and we can identify that D part is correct. Also, I have shown you this way if you know about every laws. Okay, so this Schmidt's law is correct answer. So the next question is, which one of the following is not an intensive property? So they are asking about intensive and they have given four options. So this is the confusion point, that sometimes people get confused in exam with intensive property and extensive property. So I will tell you one easy trick to learn it. Okay, so this A is temperature, B is pressure, C is volume, D is refractive index. Okay, so this first one is intensive property, and I am writing here is extensive property also. Okay, so I will give some example. So this intensive property is basically what I found, the second first two words is intensive. Okay, in in, so intensive means independent. Okay, so I can identify that this intensive is independent of the mass or matter. Okay, matter also considered in thermodynamics. And this extensive property is dependent. Okay, so we have to keep in mind only one thing, dependent on mass. That if we will remember this intensive property by in, it is independent of the mass, so we do not remember need to remember this extensive property. Okay, so I always remember this intensive property is independent of mass, because these both are in, this is beginning from in also. Okay, so intensive means independent, I learn like this. Okay, so this is independent of the mass. And the example for this independent of the mass, that is intensive property, is basically we can say the melting point is independent on the mass. These are the some characteristics: boiling point, density of the material. Okay, so pressure also independent of the mass, and temperature. Okay, and refractive index is also independent of the mass, and we can say the hardness of the material is also independent of the mass. Okay, so these are the examples, few examples. There are, this is the limited examples. I will give more idea about intensive and extensive property whenever we will start the thermodynamics part for GATE 2021. Okay, so this is the extensive property, and the example for extensive properties that depends on the mass. So we can say this is the mole mole, volume, energy. So these all are extensive property. Okay, so from here we can see that which they are asking of which one of the following is not an intensive property, means they are asking about which is extensive property. Okay, so this temperature is intensive property, this pressure is intensive property, this diffractive index is intensive property. I have already written in this list. Okay, so the volume is correct answer for this question. Volume is not intensive property, this is extensive property, and somehow it depends on the mass of the material. Okay, and it depends on the matter. Okay, so this C option is correct for this question. So the question is, the critical internal crack length in in a steel having KIC of 45 MPa root m, that is meter. This is the unit of this KIC to support a mode first stress of 400 MPa. So this is the value of stress we can identify. We have value of KIC, that is 45 MPa megapascals multiplied by root m. So this is the unit of KIC, and this sigma stress value is also given. So this we can write sigma f also. This is sigma f, that is stress to the fracture. So this is MPa, and we need to calculate the crack length. Okay, so this is the internal crack length. We need to calculate internal crack length. Okay, So the formula for this type of question is KIC, that is stress intensity factor. KIC is equals to sigma F under root of pi C. Okay, so this KIC is basically the stress intensity factor. This sigma F is the stress which is applied for mode first, and this C is surface crack length. Okay, so this is the point where students do the mistakes. This is the surface crack length, and this is something we can relate through the Griffith theory of brittle fracture. Okay, there I have told you that how to change the surface crack length into the internal crack length and vice versa. Okay, so this is the point. This C is surface crack length, and in question they are asking about internal crack length. Okay, so we need to think about these things. Okay, so the question is very easy. We will put the value and we will get the value of C. How this KIC is 45, I am putting here, and this sigma F value is 400, and this pi C is pi multiplied by C. So from here we will get root C is equals to something 0.06348. Okay, so you need to calculate one step, but I have skipped one step. Okay, so you need to do step by step during the practice session. Okay, so this is something, this is not under root. This C is equals to 0.00424029. So this is in meter, because this KIC is in meter, so this value will come in meters. Okay, so they are asking two things. They are asking about internal crack length and in millimeters. Okay, so how we can change this meter into the millimeters? This C value can be changed into millimeters by multiplying by 10 to the power 3 or 1000 into millimeter. We can change meter to millimeter by multiplying it by 10 to the power 3. So this is the unit conversion simply. Okay, so this will come in mm. So this is 4.029. This is the C value. Okay, sometimes students do the silly mistake. They will put this value in answer, that this is the crack length, this is the internal crack length, but this is wrong, because we know this C is surface crack length. I already told you this C is surface crack length, not internal crack length. So for identifying internal crack length, what we will do, we will take 2C. So if we will multiply it by 2, we will get the internal crack length. Why? Because I have already told you in Griffith theory of brittle fracture, for relation between the surface crack length and internal crack length. If you did not watch that video, you need to watch that video. That is very important concept in in mechanical metallurgy. Okay, so this answer will be around 8.05. Okay, so this is the correct answer, because they are asking about internal crack length. So I am writing the answer here. So 8.05 in mm, this is the internal crack length. Okay, so don't do the silly mistakes just because of the tricky points. That tricky point is here is that they are using internal crack length, and one tricky point is that they are asking in mm. Okay, so we understood where we can do the mistakes, and we have to rectify those mistakes during the practice session. That's why we are doing step by step. Once you will do the practice, you will be master, and you can do directly into the exams. Okay, so this is the question, and the answer is 8.05 mm internal crack length in this mode stress of 400 MPa. The next question is matching type of question. So they have given the group A, that is some element, and group B, the ore of some elements. Okay, so we have to match this A group to group B. Okay, so what I have already told you, that we will directly not jump into the options whenever we will do the matching type of questions. So before jumping onto the options, what we can do, we can write what we know about these things. Okay, so I have already told you we will try to generate our own code through these PQRS values. Okay, so what I will do, I will try to find the most common or the odd one from this list. Okay, so this PB, lead, is the most commonly which is used non-ferrous metal. I have already told in one element introduction video about this lead. You can watch that video, that is very important. Okay, and I have mentioned all the ores and minerals and the extraction route of lead in that video. Okay, so you can go through the playlist element introduction to watch that video. And this is the tin is also common, and this nickel and thorium is not that much commonly extracted. Okay, and we do not see the extraction process of this nickel and thorium in our course in GATE syllabus or in college course. Okay, so this lead is basically we can match through the galena. Okay, so this galena is PbS, that is sulfide ore of lead, and this is this we know the lead of the ore of the lead is galena, that is R, we can match R by 4. Okay, and this Sn, this Sn is basically the cassiterite. Sn, the cassiterite is the Sn ore, SnO2, that is oxide ore of cassiterite is the oxide ore of tin. Okay, so we can match this S by 2. Okay, so from here what we can do, we can eliminate the options also, but this is the practice session, so we will not do that. We will see every options, we will see everything in this question, and we will try to understand how to identify this type of questions. This is very simple questions, and it doesn't matter for us during the practice session. Okay, so we will try to avoid the silly mistakes by practicing this type of questions. So for the nickel, so this nickel is basically the ore of nickel is pentalendite, that is this is pentalendite is basically the mixture or the compound, a complex compound of nickel and iron. So we can write the formula like that. Okay, so this is the sulfide ore of nickel and iron. So nickel Fe in complex compound form it is found. So this P we can match by the 3. Okay, and the thorium is basically thorium is extracted from the monazite. Okay, monazite is the ore which is used for thorium and other rare earth metal, that is lanthanum also, neodymium also. So this and cerium, that is you have heard about cerium. This is cerium is also the FCC austenitic stabilizer in heat treatment. We use this cerium. Okay, so this monazite is basically CeLa ND and TH mixture. Okay, and we can say this is the phosphate and the silicate mixture of these type of elements. Okay, so we need not to learn about these things, I have told you in general purpose. So this monazite is something related to the this neodymium, this lanthanum, this thorium, and lanthanum, and this cerium. Okay, this is the phosphate and silicate mixture of these elements. So this thorium can be extracted through the monazite. So Q value is Q we can match by 1. Okay, so the code for our question is 3142. We will identify this is starting from 1, so we can cross. This is 4, this is 2, this is starting from C, this is 3142. So this C option is correct for this question. Okay, so this is very easy question, and this is how we eliminated every options. And during the practice session at home, you need to do only by this way. By doing this way, you will be master once in doing matchings, and you will never do the silly mistakes in exams while choosing the option, because whenever we will get the matching type of questions on a screen in GATE exam, we get excited during the exam, and we tick the options, and by mistake sometimes we choose the wrong options. That's why I am telling you to generate your own code. By generating own code, you will match the options. You will never do the silly mistakes in matching type of question, and these are the very easy questions, and every time this will give 2 marks, and if you will do wrong every time it will give 0.66 minus points. Okay, so that's why this is very easy question, but this is very this is something where we have to take do carefully. Okay, okay, so the correct option for this question is C part. So the next question is the energy of dislocation is. So basically this question is from mechanical metallurgy, and this is the easy question, but in RINL exam they can ask, because you have 100 questions in 60 minutes. So these are not easy for that exam. Okay, but this is easy whenever we will do the practice. So the energy of dislocation is, so they have given the 4 options, and also told that where B is the Berger vector. So we already know the elastic strain energy. In one of the video I already told you the elastic energy of dislocation is related to the Berger vector. This is how we can relate this Berger vector. This is shear modulus G. So elastic energy is equals to GV square. So we can say this elastic energy is proportional to the B square. Means in options we will find which is the proportional to the B square. So this is not B2, this is B square. Okay, so the energy of dislocation is this is wrong answer. This is also wrong, this is also wrong, and this is proportional to the B square. So D option is independent of B. This never can be correct, because this dislocation, this energy of dislocation is related to the this Berger vector value, that is the magnitude of that Berger vector. So we can relate this magnitude of Berger vector to the elastic strain energy by this formula, that is E is equals to GB square, GB square. This is very a simple formula, and sometimes they can give few values, and they can ask one of the values also in exam. So this is also easy for the numerical purpose, and this is something they can relate through the unit cell, that is the crystal structure. They can give the BCC, they can give the FCC. So you need to understand the Berger vector of BCC, Berger vector of FCC elements. Okay, so you have to be careful while choosing the value of this magnitude of this Berger vector. Okay, so the answer for this question is B part, that is proportional to B square. Next question is, which one of the following minerals is a source of titanium? Okay, so we will eliminate this option. So this hematite option is magnetite, ilmenite, and pyrolusite. So in this hematite, this is the most commonly ore which is used for iron production. This is Fe2O3, and B part is magnetite. So we can say this is the Fe3O4. This is also iron ore. Ilmenite we will see later on, and this pyrolusite, actually this is the manganese ore, and this is oxide ore of manganese. This is MnO2. So we can say this ilmenite is correct for titanium. Okay, so this ilmenite we will say here titanium ore. This is the titanium ore, and the formula for this ilmenite is FeTiO3. So this is basically the iron and titanium ore both, but this is good ore for titanium. And one is rutile is TiO2. So these only two ores are for titanium ore, which is most commonly used for the titanium production. Okay, so we can say that this C option is correct for this question. The mineral, so which one of the following minerals is the source of titanium? So ilmenite is the mineral that is source for titanium. So these are the type of questions they can ask in RINL exam. These are the very basics, and we can tick without doing anything. We can directly tick into the screen, because in RINL they will give 100 question, and you have to do these 100 questions within the 60 minutes. So these type of questions is very much expected in this type of question, in this type of exams. Okay, so be prepared with this type of questions. Thank you guys for your attention. Hope you guys have learned something new in this video. The number of videos in this video series of RINL-Vizag management trainee will totally depend on your feedback. If you will give the valuable feedback to us, we will try to add more and more parts in this video series before the RINL exam. So try to give the feedback in the comment section, or you can also give valuable feedback on our Instagram page. Okay, so subscribe our channel and press bell icon to get notifications for upcoming videos.